Our first problem involves a simple pendulum. Now, we know that a simple pendulum has the net force, F net equals negative kx. This is for small amplitude, okay, for amplitude much less than length. And you'll recall how we use force diagrams and a little bit of trigonometry or similar triangles equivalently to calculate the net force, or to get the idea that the net force is negative kx with k equal to mg over L in this case. So for a 5.5 kilogram mass at the end of a string of length 4 meters, in other words a simple pendulum with a mass of 0.5 kilograms and a length of 0.4 meters, we get force constant equals mg over L, and we calculate that easily, plugging in our 0.5 kilograms and our 4 meters, and we get something like 1.23 or 1.24 kilogram per second squared. And as we've seen elsewhere, kilogram per second squared is the same as a Newton per meter. Okay, now what's the period of the motion here? Okay, so we've done this. And here's how we might think about that. Okay, we've got to find the period of motion. Don't see how we do that. Well, let's not bother worrying about the period of motion just now. Let's see what we can find based on what we already know. Okay, well, let's see. We know the mass of the pendulum. We know its length. We know its force constant. Oh, yeah, we got this k, omega equals the square root of k over m thing. The central thing that you really need to understand about simple harmonic motion. There are many other things, but you don't get anywhere if you don't understand at least this and what it means. And we've, of course, seen previously what this means and how it's used to model simple harmonic motion. So all we have to do to find omega is plug in our k and our m, and we know k. Well, in general, of course, we could use this k and this m, this mass, this k, this value of k, and this mass. But we can also get a more general relationship, and you would know this based on the assignment that was due before today. K is mg over L, as we've noted up here. And the mass, of course, is m. So when you do the square root of k over m, you're doing the square root of mg over L divided by m. M divided by m, that divides out, and we're just left with g over L under the radical. So our omega turns out to be the square root of g over L, which is 9.8 meters per second squared over 4 meters in this case. And this gives us approximately 2.45 reciprocal seconds, square root of 2.45 reciprocal seconds squared. In other words, the meters divide out, leaving you a second squared in the denominator. And we write that as seconds to the negative 2. And we take the square root, we get something approximately 1.53. I think this maybe came out a little closer to 1.54. So remember, this is just an approximation. And that's going to be per second. Now, what is it per second? Well, it's radians per second. The SI unit that comes out when we're doing calculations of omega with SI units. Now we have some more explanation about where you can get a radian out of all this. This meter and this meter can both be regarded as meters of either radius or arc length accordingly, so that if this is a meter of arc length, then dividing it into a meter of radius gives it a radian squared of angular displacement, giving us then the radians per second. But we don't need to worry too much about that. That will come out in radians per second, and always when you do omega equals square root of k over m, if you have SI units for all quantities, this will come out in radians per second. Of course, you're always going to get the seconds, and you want to work through the algebra of that process. Okay, so there's our 1.53 radians per second. Now, the question, though, didn't ask for the number of radians, it asked for the period of the motion. And I note that my M there is a little anemic. Let's make that look a little more like an M. And that O looks a whole lot like a U. Let's fix that before we go on. Okay, now, we want to know the period, okay? We've used what we can to find out what we can, and we do get this angular frequency, this 1.53 radians per second. Well, let's go back to the idea of a reference circle. We have a reference circle where this point moves around the reference circle just the way the straw on the beam moves around the circle, mimicking the motion, the back and forth motion of the pendulum that's right behind it. And the pendulum completes an oscillation. When these things are synchronized, the pendulum will complete an oscillation in the time it takes the reference point to go around the circle. And the reference point moves with angular velocity omega, where omega is what we call the angular frequency of the simple harmonic motion. Well, the period is how long it takes us to complete that then. Okay, the period is the time it takes for one complete revolution, which is one complete back and forth oscillation of the pendulum. The angle around the circle is 2 pi radians. So how long does it take to go around the circle at angular velocity omega? Well, the time around the circle will be 2 pi divided by omega. In this case, that means, of course, 2 pi radians divided by omega. Radian being the default unit of angle. We didn't have to write it here, but we're going to write it. Yeah, we have the option. We can write it or not. That's the advantage of the default unit. So 2 pi over omega means 2 pi radians over 1.53 radians per second. When we divide that, the radians divide the radians. Reciprocal second in the denominator becomes a second after when we divide. and we just do the arithmetic, and we get something very close to 4.0 seconds. So there's the period of our motion. Now note that we did have one question: how does meters per second squared over meters give us reciprocal seconds squared? So I wrote that out. Meters divided by seconds squared divided by meters means meters over seconds squared. Division by meters means multiplication by reciprocal meters, which is 1 over squared seconds then, the meters dividing out, giving us reciprocal seconds squared, or seconds to the negative 2. So once again, for pendulum, we determine that F net equals negative kx, where k equals mg over L, as we've shown earlier. And then for a mass of 0.5 kilograms, length of 0.4 meters, we get our value of k. We could use this value of k and this mass directly in this relationship. But for a pendulum, since k is always mg over L, we can write the expression for omega this way, and that simplifies to the square root of g over L, and that's what we chose to use in this situation. But we could have used this and this equally well. Then from that, we determined that from the reference circle picture, that since we're moving at angular velocity omega and complete a cycle in the time it takes to go through 2 pi radians, the time it takes to complete a cycle here is 2 pi radians divided by the 1.53 radians per second, or very close to 4.0 seconds. An even briefer synopsis: we had the information to determine the force constant, so we could determine the angular frequency using this relationship. But for a pendulum, that relationship reduces to the square root of g over L, where L is the length, so we really didn't even need the mass to get this. We got the angular frequency and used that to easily calculate the time it takes to complete a cycle, or the period of the pendulum.